let's study about the vibration analysis of a truck cab supported by springs. This report analyzes the vibrational characters of a truck cab assumed to be supported by 4 identical springs. Okay, imagine there are some 4 identical springs that supports the cab. Okay, and objective is to determine the resonant frequency of the cab and amplitude of vibration when subject to a sinusoidal displacement. So there is some sinusoidal displacement is going to happen, so we need to find out the resonant frequency as well as the amplitude of vibration. That's our objective. That's fine. Problem statement: a truck cab with mass of 1500, so mass we know, that's 1500 kg, supported by 4 springs. Each spring stiffness also we know, and the displacement input into the system is, this is the displacement input. It's a forcing function 0.05, it's a displacement amplitude, and sine omega, this is a forcing frequency t. Determine the resonant frequency and calculate the amplitude of vibration of the cab under the given input. So mass we know, spring also we know, total stiffness, the displacement also we know, forcing frequency is given. Okay, theoretical background: the system can be modeled as a single degree of freedom system with undergoing a forced vibration. So this is the forced vibration. If this is 0, then that will become transient response, that becomes only a natural frequency. Since we have the forcing frequency, forcing function, after few seconds, once the transient response dies out, this forcing frequency is going to stay. So mass, total stiffness, p naught, omega x, all this is known. Static deflection we know, that's force by force divided by stiffness will gives displacement. So the natural frequency is square root of k by m. Resonant frequency is fn equal to omega n by 2 pi. That's the resonance frequency. Frequency ratio we know, beta w by omega n. So magnification factor is nothing but 1 by 1 minus beta squared. Beta is nothing but this frequency ratio. Next one is amplitude of vibration. Once we know the magnification factor, we can multiply the static deflection by magnification factor. So the step 1, we calculate the p naught, that we know k into delta, and calculate natural frequency, resonant frequency. So resonant frequency is 2.85. Our forcing frequency we know, that's 6. So the ratio between the forcing frequency and natural frequency becomes 0.335. That means it's close to 1, not close, very close to 1, but it's 0.335. That means like beta is less than 1. So magnification factor becomes 1.12. If the beta is greater than 1, then that becomes, if it is equal to 1, magnification factor becomes infinity. If it's greater than 1, it becomes negative. So displacement amplitude will be less only. So since here it is forcing, the beta ratio is very less than 1, too much less than 1, and the total stiffness we know, natural frequency, resonant frequency, beta frequency ratio, magnification factor, vibration amplitude, and the resonant frequency, natural frequency is calculated to be 2.85. Excitation frequency is 6 radian per second, that's 0.95. That 0.95 is much less than the natural frequency. The system is operating below resonance. The magnification factor being slightly above 1 indicates a mild amplification of the vibration amplitude compared to the static deflection. Amplitude of vibration is 0.0563 against the initial displacement of 0.05 due to the forced vibration response. There is one thing like we need to understand: if beta is less than 1, the system motion is dominated by natural frequency response with forced response oscillation superimposed. If equal to 1, the resonance occurs, causing maximum amplitude. If it is greater than 1, the forced response amplitude reduces below the static deflection. So we will discuss about this, whatever the problems we had, we will have a group discussion. Alright, let's carefully analyze this vibration problem involving truck cab. The mass we know 1500 kg, supported by 4 springs with stiffness 120 kN. The first step is to find the total stiffness of the spring system. Since the cab rests on all 4 springs simultaneously, so we can find out the total stiffness by adding up all directly. So the total stiffness becomes 4 into 120,000, so 480,000. So when the springs are in parallel, we add up all those directly. So we converted kilonewton meter to Newton meter by multiplying 1000. The cab is modeled as a mass and attached to the spring stiffness of this much. So now the displacement input we know from the accelerator is 0.05 sine 6 t, that's meters. So 0.05 is the amplitude, and the angular frequency we know 6, that's the radian per second. So this is a sinusoidal input, which means the system is forced to vibrate at this frequency. So this is the frequency at which system is forced to vibrate. How do we represent the forcing function in the equation of motion? So we know the forcing function, the equation of motion. This is the equation of motion with a forced vibration with no damping. Since there is no damping, the transient vibration is not going to die out. It would go on forever. If there is a damping, the transient response would die out, and it will the transient decay would happen. After some time, the transient response will fade away. Then only the steady state response is going to be staying. So x is the displacement of the mass, and p naught is the amplitude of the external force acting on the system. So but the input is the displacement, right, not a force. How do we find p naught? We know there's a relation between p naught and stiffness and displacement. From that we can come to the force. So since the input is displacement at a base, the equivalent force is exerted on the system is, we can find it out. This comes from the fact that the spring force is proportional to the displacement. That's right. I guess we need to find the natural frequency, right? Correct. Natural frequency we can calculate this way, 17.9 radian per second. How about converting to hertz? So we can convert to the hertz by dividing simply divide by 2 pi, we get in hertz. So the system's natural frequency is 2.85 cycles per second. This is 2.85 cycles per second. Forcing frequency we know that is 6 radians per second. Converting into hertz is 0.95. So the forcing frequency is much less than the natural frequency. Since the forcing frequency is less than the natural frequency, the system is operating below the resonance. So could you explain why that matters? Sure, the system exhibits different behavior depending on the ratio between the forcing frequency and natural frequency. We define that ratio as frequency ratio. Depending upon the frequency ratio, the system is going to behave differently. So this is the forcing frequency, frequency ratio. If frequency ratio is less than 1, the system is below resonance, and the vibration amplitude is generally higher than the static deflection, but not dangerously large. You can see that here. You can see here, if this is the motion in phase with the excitation, since the beta ratio, this is the beta ratio, it's less than 1, so it's operating this way. So the static deflection is 1. Magnification factor increases as you approach to resonance, and if it is the ratio is going more than 1, then the response is the amplitude decreases, and the motion also, it's out of phase. So when the beta equal to 1, the resonance occurs, causing potentially huge amplitudes. If the beta is greater than 1, the system response amplitude decreases and lags the forcing function, decreases. That's why you can see this is the decreasing value, and it is lagging by 180 degree. That means it's almost like the opposite. How do we quantify the amplitude of vibration? How do we quantify the amplitude of vibration? We know the magnification factor, 1 divided by 1 minus beta squared. From that we will come to this, the magnification factor. That's almost 12.7% more. The system amplifies the displacement. Initial displacement, we know the system is going to amplify the initial displacement by roughly 13%. The static deflection we know 0.05. The total amplitude of that vibration we will know by magnification factor. If you multiply those, almost 13% is going to be higher side. So the cap vibrates at an amplitude of 5.63 centimeter. Initially it was 5 centimeter, it becomes 5.63. Exactly, this is the steady state amplitude after the transient effect dies out. Speaking of transient effects, what happens initially? Good question. The complete solution of a differential equation is the sum of transient and steady state vibration components, right? So x of t equal to x sine omega t minus phase angle and transient terms. The transient terms decay with time if damping is present. What about the phase difference? For beta is less than 1, the response is approximately in phase with forcing function. As the frequency increases past resonance, the phase lag approaches 180 degrees. Why is that so? If the frequency is more, then it's for the mass to keep up with the frequency, it's difficult, because the inertia is going to resist, damping also going to resist. If the frequency is very high, for the system to keep up with that frequency, it's difficult. That's why it becomes like 180 degree approach. Lagging is happening in the phase angle. How does the damping affect all of this? Damping reduces the amplitude near resonance and causes transient terms to decay faster. The system won't vibrate endlessly. If there is no damping, it's going to vibrate endlessly. Our problems use damping as a simplified model. Real systems always have some damping. Can this analysis happen in suspension design? Knowing the natural frequency helps avoid resonance in common forcing frequencies like road bumps or engine vibrations. We know that what if the input frequency was close to 78.9? If it's close to the natural frequency, that would cause resonance, leading to large vibrations, possible damage. How can we prevent resonance? By adding damping, chain stiffness, or mass, and try to shift the natural frequency or avoid the excitation frequency near omega n. Does the magnification factor formula change with damping? Yes, of course. It becomes more complex, involving damping ratio. This damping ratio is there, right? That involves damping lowers peak at resonance. With the because of the damping, it lowers. Otherwise, it would go infinite. Back to our problem. The initial displacement is 0.05. Is that output vibration amplitude x larger or small? In this case, slightly larger, which is acceptable for this system. What about the force transferred to the cab frame? The dynamic forces can be estimated by multiplying the vibration amplitude by stiffness and mass acceleration. We know the vibration amplitude, we can multiply the stiffness, then we can get the forces. Are there any safety concerns? Only if the vibration amplitude or forces approach damaging level, but here system is safe. Row irregularities cause the input frequencies near resonance possible. Designers choose the suspension parameters to avoid this. What practical steps do engineers take to reduce vibration? Use damping, increase stiffness, mass, or vibration isolators. What about nonlinear effects? Nonlinearity is complicated analysis, but linear approximation is valid for small vibrations. We have gone through the case where beta is less than 1, but what happens if beta is greater than 1? What if the forcing frequency is higher than the natural frequency? That's interesting region, right? When the beta ratio is greater than, means system starts to behave very differently. The steady state amplitude decreases. You see, the steady state amplitude decreases. Why is that decreasing? Why it decreases? Because even though input is very strong or faster, the vibration amplitude becomes smaller. Yes, because at high frequency, the system cannot respond quickly enough. You understand? It cannot respond quickly enough. It lags behind heavily because the mass moves less because of inertia dominates. So the in region where the beta is greater than 1, inertia dominates. That sounds counterintuitive. Can you show me how? The remember the magnification factor? Yes, if beta is greater than 1 means beta squared minus 1. So beta increases, magnification decreases rapidly, 33%, 12%, like that. If beta equal to 33%, if it is 3.125, it decreases. So above the twice the natural frequency response, even if it is less than the static reflection is. That's crucial point. When beta is greater than square root, the dynamic amplitude is actually less than the static deflection. That means the vibration is attenuated. Is there a physical explanation for this drop? Yes. Think about a mouse trying to follow a rapid sinusoidal input. If it is heavy mass, it cannot easily keep up with the higher frequency because its own mass resists the change in direction so rapidly, right? Its own mass resists change in direction. But at higher frequencies, it cannot keep up. At lower frequencies, it can follow the frequency closely, follow the force closely. The system can follow the force very closely if it is a lower frequency. If the system cannot follow the force if the frequency is very high, because the system's own mass is going to resist. That's why when the beta ratio is greater than 1, and the amplitude decreases. So good question. The phase lag is also increasing dramatically. At the beta equal to 1, the phase lag is 90 degree. Beta greater than 1, it approaches 180. That's almost out of phase. It's out of sync. When input goes up, the system goes down. Vice versa, that's if beta is greater than 1. So the motion almost cancels out the excitation. Yes, that's why in certain cases, operating above the natural frequency is preferable, especially in systems designed for vibration isolation. Is this why engines machines sometimes are mounted on soft close stiffness isolators? That could be. So here, technical summary: what happens if beta ratio is greater than 1? Amplitude decreases rapidly as the beta increases. We have seen that if beta is 2, 33%, if beta is 3, only 0.125. And magnification factor, that becomes 1 divided by beta square minus 1, the inverse square drop. Phase difference almost 180 degree. Response out of phase with input. Displacement response becomes smaller than static deflection when beta is greater than 2. Physical effect: inertial resistance dominates. System lags and filters the input. Design implication: useful for vibration isolation. If you are designing a vehicle inspection, you usually want to avoid operating near beta equal to 1 since that's resonance. If you are building a vibrator sensor, you see maximize beta, operating the system above the resonance where the resonance was attenuated. Systems like machine mouse make often tuned to ensure beta is greater than 2. So here you can see this is the beta ratio. Beta ratio, if it goes up, the motion becomes out of sync, and also the amplitude reduces, like when it's 233 percentage, 12.5 percentage, like that. When if it is less than 1, it follows the phase. The system follows the force, because low frequency it can come very slowly, so system also can follow. The inertia is not dominant here, but inertia is dominating here, that's why it becomes less.